research, the latest thinking, and really boil it down to the key insights for you. Today we're tackling, well, one of the biggest puzzles in physics, trying to bring general relativity and quantum mechanics together. There's this real pull in science towards simplicity, isn't there? This idea of reductionism, just breaking things down, like how we went from seeing stuff as just matter to molecules, then atoms, then protons and neutrons, and now quarks and leptons. It feels like this straight line downward.
Yeah, it really does. And that feeling, that apparent progression, it often leads people to ask, well, what if the answer to quantum gravity, this huge gap between Einstein's GR and quantum mechanics, QM, what if it's actually pretty simple?
Simple how?
Like, what if it's just the next step down, just discovering even tinier particles, maybe smaller than the Planck length? It sounds neat, right? Very appealing.
Yeah, that does sound appealing. And that's exactly what we're diving into today. We're really going to scrutinize that specific hypothesis. Because our argument, based on everything we've looked at, is that the gap between GR and QM isn't just a little crack you can paper over. It's fundamental. It needs a whole new way of thinking, a revolutionary structure, not just, adding another floor to the building.
That really is the crux of it. And maybe before we go further, let's just pin down what simplicity means here. In physics, it's not really about being easy to understand or feeling intuitive.
Right, like Occam's razor, don't multiply entities beyond necessity. It's about fewest assumptions.
Exactly. But it's not just about sticking to what's familiar. Einstein had that great line, right? A theory should be as simple as possible, but not simpler.
Yeah, that quote really nails it. True scientific simplicity isn't about how easy the concepts feel in your head. It's about how much the theory explains. Unifying lots of different things with just a few core ideas, even if those ideas themselves are, well, kind of weird and counterintuitive at first glance.
Precisely. So a theory that just ignores huge inconsistencies, like the ones between GR and QM, well, it doesn't really simple in that powerful scientific sense. It's just incomplete.
Okay, so let's look at that historical analogy again, going smaller and smaller. You said it seems like a straight march down.
That's the surface story, yeah. A very compelling narrative.
But you're saying the real story underneath wasn't just finding smaller thing.
Not at all. When you actually unpack it, the journey was punctuated by these huge conceptual earthquakes, revolutions. We had to throw out old ways of thinking and invent entirely new physics.
Okay, let's take atoms. Dalton thought they were indivisible, the end of the line.
Early 1800s, yeah. Solid little balls.
But then, turn of the 20th century, boom. J.J. Thomson finds the electron in 97. Rutherford finds the nucleus in 1911. Suddenly, atoms have parts.
And that immediately created a massive theoretical problem. The model they had, like electrons orbiting the nucleus like planets.
The planetary model.
Yeah, classically, it just didn't work. The electron should radiate energy and spiral into the nucleus almost instantly. It was completely unstable according to the physics they knew.
So the fix wasn't just a small adjustment.
No way. The fix was quantum mechanics. Energy coming in packets, quantization, wave-particle duality, probabilities. These ideas were totally bizarre, completely alien to classical physics. It wasn't an extension, it was an overthrow.
Okay, fast forward a bit. Mid-20th century, particle accelerators are finding tons of new particles. The particle zoo, they called it. Things were getting messy again, not simpler.
Oh, incredibly messy. Dozens of supposedly elementary particles. It felt like chaos.
So what brought order to that?
That was Murray Gell-Mann in 1964 with the quark model. Suddenly, things like protons and neutrons weren't fundamental anymore. They were made of quarks.
So smaller particles again?
Yes, but again, it wasn't just finding smaller particles. It demanded a whole new theoretical framework. Quantum chromodynamics, or QCD. This involved a new kind of charge, color charge, nothing to do with visible color, of course.
It's just a quantum property.
Right. And it involved this abstract mathematical symmetry, SU3, dictating how quarks interact via gluons. And quarks themselves had really weird properties, like confinement. You can never actually see a quark by itself. They're always stuck inside larger particles.
So the big win for the standard model, which includes QCD, isn't just listing parts. It's the unification, right?
No.
Bringing electromagnetism, the weak force, the strong force together.
Exactly. It explains why things are the way they are, based on underlying symmetries and principles. It's unification, not just reduction.
And gravity.
Gravity is the elephant in the room, the one force left out of this otherwise incredibly successful standard model.
What else is different now compared to those historical leaps? You mentioned experimental evidence.
That's a crucial difference. Each major revolution in quantum mechanics, the quark model, was driven by specific experimental results that the old theories just couldn't explain. Blackbody radiation, the photoelectric effect, those deep inelastic scattering experiments at SLAC that basically saw quarks inside protons.
We had data pointing the way.
We had data screaming that something was wrong. But for quantum gravity, we don't have that direct experimental prod right now. The energy scale, where we expect quantum gravity effects to become obvious, the Planck scale, is just astronomically high, far beyond anything we can reach.
So we're relying more on mathematical consistency, theoretical principles.
Exactly. Which makes the historical analogy, when you look closely, argue against a simple extension. History shows deeper levels required radically new ideas, often prompted by data we currently lack, for quantum gravity.
Okay, so history suggests revolution. What are the actual fundamental roadblocks? Why can't we just say find a graviton particle and plug it into our existing quantum field theory framework? You said there are irreconcilable conflicts.
Yes, and they run deep. It's about how GR and QM describe the very fabric of reality in fundamentally contradictory ways.
Let's start with spacetime. How does GR see it?
In GR, spacetime is, well, it's the star of the show. It's this dynamic, smooth, four-dimensional sheet, if you like. It curves and warps in response to mass and energy.
And that curvature is gravity.
Precisely. Spacetime tells matter how to move, and matter tells spacetime how to curve. It's an active player.
Okay, and quantum field theory, or QFT, how does it treat spacetime?
Totally differently. For QFT, spacetime is just the stage. It's passive, fixed, rigid, usually flat, like the background grid on which all the particle interactions, the probability waves takes place. The stage itself doesn't really participate.
And that difference leads to major problems, like the problem of time.
Oh, absolutely. This might be the deepest conflict. In quantum mechanics, time is treated as this universal, absolute parameter, like a master clock ticking away uniformly for the whole universe, marking the evolution of quantum states.
But GR says,
GR throws that whole idea out. There is no universal master clock. Time is relative. It's dynamical. It gets stretched and squeezed by gravity. Clocks literally tick at different rates depending on the gravitational field, slower down here near sea level, faster up on a mountain.
so a unified theory has to answer, what is time? Is it the quantum clock or GR's stretchy fabric?
It's a fundamental question we don't have an answer to yet, and this relates directly to another clash: background dependence versus independence.
Okay, what does that mean?
Well, QFT, because it assumes that fixed stage is background dependent. You have to put in a space-time structure before you can do any calculations.
Like assuming a flat stage to start with.
Right. But GR is background independent. There's no pre-existing stage because space-time is the gravitational field. It creates itself, so to speak. So trying to use standard QFT methods to quantize gravity, it's like trying to quantize the stage itself. Using tools designed only for the actors on the stage, the tools just aren't right for the job.
And then there's this mathematical nightmare, non-renormalizability. You mentioned that standard QFTs handle infinities using renormalization.
Yes. It sounds technical, but it's crucial. In calculations for electromagnetism or the strong and weak forces, you inevitably run into infinite values. But there's a systematic procedure, renormalization, that lets you sort of absorb these infinities into a few physical quantities you measure experimentally, like the mass and charge of the electron.
And once you do that, the theory gives finite, testable predictions.
Exactly. It makes the theories incredibly powerful and predictive.
But gravity?
Gravity is the disaster story here. When you try to apply the same QFT approach, treating gravity as mediated by a hypothetical graviton particle, the math just explodes. It's non-renormalizable.
Meaning?
Meaning you don't just get a few manageable infinities, you get an infinite number of different kinds of infinities popping up at every stage of the calculation. To cancel them all out, you'd need to introduce an infinite number of parameters that you'd have to measure.
Which makes the theory useless.
Completely useless. A theory that needs an infinite number of inputs to make a prediction has zero predictive power. It's physically meaningless.
Is there a deeper reason why gravity fails so spectacularly here?
Yes. It comes back to gravity's unique nature. Gravity interacts with everything that has energy, including itself. The gravitational field carries energy, and that energy creates more gravity. It's this self-interaction, this feedback loop, that generates the uncontrollable cascade of infinities.
Unlike, say, photons and electromagnetism.
Right. Photons carry the electromagnetic force, but they don't have electric charge themselves, so they don't directly interact with each other in the same problematic way. Gravity talks to itself, and in the quantum realm, that conversation gets infinitely loud.
So GR isn't wrong exactly, but it can't be the final word. It's an effective field theory.
That's the modern understanding. It's a brilliant, incredibly accurate description of gravity at large scales and lower energies, way bigger than the Planck scale. But the math, the non-renormalizability, tells us it must break down at extreme energies or tiny distances. It's an approximation, a placeholder for a deeper theory.
So trying to just extend it into that quantum regime is fundamentally flawed because the theory itself signals its own breakdown there.
Precisely. You can't just tweak a theory that fundamentally tells you it's incomplete at the scale you're interested in.
Maybe let's quickly contrast the forces again, just to highlight gravity's oddness.
Sure, you got the strong force, acts on color charge, gluons mediate, strength 1, range is tiny, nuclear-sized, renormalizable.
Acts on electric charge, photons mediate, strength 10 to infinite range, renormalizable.
Acts on flavor, WZ bosons mediate, strength 10.6, range even tinier, renormalizable.
Acts on mass energy, maybe gravitons mediate, strength incredibly weak, 1038, infinite range, but crucially, not renormalizable.
That single no for gravity really stands out. It's fundamentally different in how it behaves quantum mechanically.
It shouts from the rooftops that gravity is different. That self-interaction makes it mathematically untamable within the standard QFT framework. We need something new.
Okay, so we've hit historical arguments, mathematical barriers. Now, the Planck wall. The initial thought might be, okay, it's small, but maybe we'll eventually probe beyond it. You're saying it's more than just a technical challenge.
Much more. The Planck scale, Planck length, Planck time, Planck energy isn't just another milestone. It seems to represent a fundamental boundary where our concepts of space, time, and even measurement itself start to dissolve.
And these Planck units, they're not arbitrary, right? They come from fundamental constants.
Exactly. They're unique because they're derived by combining three of the most fundamental constants of nature. C, the speed of light from relativity. G, Newton's gravitational constant from gravity. And cool, the reduced Planck constant from quantum mechanics.
The fact that you need all three
is a huge flag. It signals this is the scale where relativity, gravity, and quantum mechanics absolutely must collide and merge. The Planck length, for instance, is about 1.6 by 1035 meters. Unimaginably tiny.
Okay, walk us through that thought experiment. How does trying to measure something at the Planck length lead to a paradox?
Right. So imagine you want to see what's happening at a very, very small distance. Let's call it x. To do that, you need a probe like a photon with a wavelength, at least as small as that distance. Basic optics.
A shorter wavelength means you can see smaller details.
Exactly. But here comes quantum mechanics. Heisenberg's uncertainty principle tells us that a very short wavelength means the photon must have incredibly high momentum and therefore incredibly high energy, EEPC.
Okay, so to probe tiny distances, you need a super high energy photon.
Now, bring in general relativity. GR tells us that if you concentrate enough energy, or mass, into a small enough region of space, you create a black hole. The boundary of no return is the Schwarzschild radius.
Okay, so where's the collision?
The collision happens right at the Planck length. If you calculate the energy needed for a photon to have a wavelength equal to the Planck length, and then you calculate the size of the black hole that much energy would create,
don't tell me.
the Schwarzschild radius of that black hole turns out to be roughly equal to the Planck length itself. To measure the Planck length, you need so much energy that you inevitably create a black hole about that size, trapping the information you were trying to get out.
Whoa. So the very act of looking prevents you from seeing.
Precisely. It's not just that our machines aren't good enough. The laws of physics themselves seem to conspire to prevent us from resolving distances smaller than the Planck length. It suggests a fundamental limit.
So what does that do to our picture of space-time down there? If you can't measure it, does it even exist in the way we think?
That's the profound implication. It strongly suggests that the idea of a smooth, continuous space-time, the basis of GR, breaks down completely. It's not a gentle background anymore. The common picture is quantum foam.
Quantum foam?
Yeah, a chaotic, turbulent sea where space-time itself is undergoing violent quantum fluctuations. Tiny virtual black holes and wormholes might be constantly popping in and out of existence. The very notion of a precise location or a definite distance becomes fuzzy, maybe even meaningless.
And it's important to stress, this isn't like a tiny pixel, right? It's not that space is made of Planck-sized cubes.
That's a common misunderstanding, yeah. The Planck length, derived this way, is the scale where our current theories and the classical concept of continuous distance definitively fail. It's the boundary of our understanding, the point where smooth geometry dissolves. Saying there's a particle smaller than the Planck length doesn't make much sense if the space it would exist in isn't smooth and well-defined at that scale.
So bringing it together, the math breaks down, Non-Renormalizability.
Mm.
And the physical act of measurement seems to break down too, all converging on this Planck scale. Both roads lead to the same conclusion. Space-time, as we know it, can't be fundamental.
Exactly. Smooth spacetime has to be an emergent phenomenon, an approximation of something deeper and weirder happening underneath, like the smooth surface of a lake emerging from the chaotic jiggling of countless water molecules.
Okay, so if a simple extension is off the table, we need these radical new frameworks. You mentioned string theory and loot quantum gravity as the main contenders. They must be offering completely different pictures then.
Oh, completely different philosophies and starting points. They really highlight why the answer has to be revolutionary.
Let's tackle string theory first. The core idea is particles aren't points.
Right. String theory says the fundamental building blocks aren't zero-dimensional points, but tiny, vibrating, one-dimensional filaments strings. Think of them like incredibly small rubber bands vibrating at the Planck scale.
And how does that help with those infinities that plagued quantum gravity before?
Because strings aren't points, they're extended objects. When they interact, they don't meet at a single infinitesimal point in spacetime. They interact over a small region, effectively smearing out the interaction. This smoothing effect naturally tames the infinities that arise from point-particle interactions in QFT.
Okay, so it potentially solves the infinity problem.
What about?
Unification.
This is where string theory really shines, conceptually. The different ways a string can vibrate, its different notes or harmonics correspond to different elementary particles. So an electron is one vibration pattern, a quark is another, a photon is another.
They're all just different tunes played on the same fundamental string.
Exactly. And here's the amazing part. One particular vibrational mode of a closed loop of string naturally has precisely the properties required for the hypothetical quantum of gravity, massless spin 2. So gravity isn't something you add in, it's an inevitable consequence of the theory. That's why it's often called a candidate theory of everything.
That sounds incredibly elegant.
But
There's always a but, isn't there? The baggage, as you called it, extra dimensions.
yes, for the math to be consistent, string theory doesn't work in our familiar four space-time dimensions, 3 space, 1 time. It requires 10, or in the case of the overarching M theory, 11 dimensions.
So where are the other 6 or 7?
The idea is they're compactified, curled up into incredibly tiny, complex shapes called Calabi-Yau manifolds at every point in our familiar space. So small we can't detect them directly. Think of the garden hose. From far away, it looks one-dimensional, but up close, you see it has a circular dimension curled up.
Okay, curled up dimensions. What else? Supersymmetry.
Supersymmetry, or CUSY, is another crucial ingredient. It's a hypothesized symmetry that pairs every known particle, fermions like electrons and quarks, with a corresponding superpartner particle, bosons, and vice versa. So there should be electrons and quarks.
And we haven't found any of these superpartners.
Not yet, despite extensive searches at places like the Large Hadron Collider. That's a significant challenge for the theory.
And you mentioned M theory in a landscape.
Right. There are actually 5 consistent versions of string theory in 10 dimensions. M theory in 11 dimensions is thought to unify them. They're like different corners of this larger theory. M theory also includes higher dimensional objects called branes, like membranes. The landscape problem comes from the huge number of ways those extra dimensions can be compactified. Maybe 8,500 or even more possibilities. Each way could lead to a universe with different physical laws, making it incredibly hard to extract unique, testable predictions for our universe.
Okay, so that's string theory.
Yeah.
Aims for everything, requires extra dimensions, and HUI faces the landscape challenge.
What about loop quantum gravity? You said it's a different approach.
Completely different philosophy. LQG doesn't start from particle physics and try to get gravity. It starts directly with Einstein's general relativity and tries to apply quantum principles to it, fully embracing its background independence from the get-go. Its main goal is a consistent quantum theory of gravity itself.
And its big idea is that space-time is fundamentally discrete, not just that our measurements fail. Exactly. In LQG, spacetime isn't a smooth continuum that breaks down. It's fundamentally built from discrete chunks, or atoms, of space and time at the Planck scale. This discreteness isn't put in by hand, it emerges from the quantization process itself.
How does it represent this? Spin networks.
Right. Quantum states of the gravitational field, which is spacetime geometry in this view, are described by mathematical structures called spin networks. These are like graphs with nodes and links. The links carry information representing fundamental units of area, and the nodes represent fundamental units of volume.
So area and volume themselves come in minimum packet sizes, like the Planck area.
Precisely. There's a smallest possible non-zero area, a smallest possible non-zero volume. You can't subdivide space infinitely. This inherent discreteness naturally avoids the infinities that plague other approaches because there are no infinitely small
And
points.
because it starts with GR, it's automatically background independent.
Yes. The spin network is the quantum geometry. There's no background stage. Space itself is defined by the connections and relationships within this network. The evolution of these networks through time is described by something called spin foams.
Does LQG make any unique predictions we could potentially test?
The most famous one relates to the Big Bang. LQG suggests there wasn't an initial singularity, an infinitely dense point. Instead, as the universe was collapsing before the Big Bang, quantum gravity effects created a powerful repulsive force at the Planck density, causing it to bounce back out. So a big bounce instead of a big bang.
That's a dramatic difference. Does LQG have its own challenges?
Oh, certainly. One major challenge is showing convincingly how the smooth, classical spacetime of GR emerges from this discrete quantum structure at large scales. That's called the classical limit problem. And fully incorporating matter, like electrons and quarks, into the framework is also an ongoing area of research.
Wow. So just comparing them quickly. String theory starts with quantum particle strings, aims for everything, needs extra dimensions, and SUSY predicts the graviton naturally. LQG starts with Yar's geometry, aims just for quantum gravity, predicts discrete spacetime and a big bounce, and is background independent from the start.
That's a good summary. They have fundamentally different entities, starting points, goals, and pictures of reality at the Planck scale.
Okay, let's wrap this up. We started asking if the answer to quantum gravity could be simple, just more reductionism, finding particles below the Planck length. But our dive really shows why that's just not on the cards.
No. History argues against it, showing revolutions were needed. The core theories, GR and QM, clash fundamentally on the nature of space and time.
The math breaks down with infinities when you try the simple approach.
And the Planck scale itself appears to be a real physical boundary where measurement and maybe even space-time itself dissolves into quantum foam. You can't just assume a smooth background to find smaller particles in.
So the path forward has to be a reconstruction, not just an extension. But you mentioned the search for simplicity isn't wrong, just deeper.
Exactly. The simplicity physicists are searching for isn't about being easy or familiar. It's about finding those minimal, powerful underlying principles that can unify disparate phenomena. Think about GR again. The simple idea of the principle of equivalence leads to the whole complex structure of curved spacetime. That's the kind of deep simplicity we're after for quantum gravity.
Finding the core idea from which both GR and the standard model naturally emerge.
That's the dream, a single framework where they appear as different aspects or different limits of one underlying reality.
And maybe the most mind-bending implication shared by candidates like string theory and LQG is
It's that space and time themselves, the very stage of our existence, are likely not fundamental. They're emergent. Like wetness is an emergent property of many water molecules. Maybe space-time is an emergent property of something more fundamental happening beneath.
which throws everything we take for granted into question. Locality, cause and effect, maybe even the flow of time itself.
It really does. If space-time is emergent, what does that mean for our deepest intuitions about reality?
Which leaves you, the listener, with maybe the biggest question. If space and time emerge, what are they emerging from? And that problem of time, GR's Strecky time versus QM's absolute clock, that still feels like the rawest nerve, doesn't it?
It feels like perhaps the deepest clue we have. Solving that conflict might force us to completely rethink what existence even means. Whatever the final theory looks like, it won't just be chapter X of 20th century physics.
It'll be book 2,
Yeah.
a whole new story.